In this video, we present an overview of our work on a predictive safety filter for learning-based racing. Deploying controllers that lack safety guarantees, like those often found in learning-based methods, can be dangerous for safety-critical systems, such as in vehicle racing. We introduce a safety filter designed for a vehicle system that fits between the controller and the vehicle and is able to render the closed-loop system safe, meaning constraint satisfaction is ensured for all future time steps. In the context of racing, our main safety objective is to keep the vehicle inside track boundaries. If a vehicle trajectory exists within the constraints after applying the learning input, then we consider it safe and can apply it to the system without interference. Given an unsafe learning input, so an input that would force the system to violate constraints in the future, we want the safety filter to compute an alternate input that is able to keep the vehicle within track limits. We formulate the safety filter as a model predictive controller, subject to system dynamics and state and input constraints, with a cost function that minimizes the difference between the proposed learning input and the initial MPC control value. We can then take that initial control value as our safe input. The optimal solution given a learning input that is safe is to set the initial control value to the learning input, resulting in zero cost. If the learning input is unsafe, the problem will find the closest possible control value that does not cause a constraint violation along the horizon. We additionally penalize the input rate of change, helping to encourage a smoother control trajectory. We constrain the terminal state of the trajectory to an invariant safe set, which is a set for which we know the system will stay inside indefinitely when subject to a known local control law, and provides a safety guarantee for the system. To provide good performance during aggressive racing maneuvers, we use a dynamic bicycle vehicle model with nonlinear Pacheco tire forces. We solve the problem with a fast, real-time iteration SQP method from Akados, and we generate a permissive safe set used for the terminal constraint. We introduce an optimization-based design procedure for computing this terminal set for the dynamic vehicle model, providing invariance for track segments of constant curvature. We use a vehicle state that is parameterized by the track curvature, and propose a constant linear control law to stabilize the vehicle around the track's centerline for a grid of curvature values. We solve for this control law and the largest corresponding ellipsoidal invariant set using semi-definite programming, and perform an additional verification optimization problem to ensure invariance holds across the continuous range of curvatures. We now show two demo applications of use cases for a safety filter of this form. First, we see a human driver as the learning controller, commanding the vehicle by joystick, with original and safe inputs shown in the plots on the right, and the safety filter trajectory overlaid in blue. When the driver acts safely initially, there is minimal intervention from the safety filter. However, as the driver behaves dangerously, the safety filter must deviate from the desired control signal, applying different inputs to keep the vehicle in bounds. Next, we demonstrate safe imitation learning, using the iterative dagger method along with the safety filter to provide a safe, automated training session for the physical system. An expert MPC racing controller is used to build an initial dataset of state-action pairs. We train a feed-forward neural network on this data, then deploy the network as the controller, which performs poorly. However, the safety filter successfully keeps the vehicle in bounds, preventing it from cutting corners. We label the visited states with the expert policy, add to the training data, and retrain the network. This is repeated for several iterations, after which the network closely mimics the expert, requiring no major safety interventions. We have demonstrated a real-time capable predictive safety filter that is able to provide safety for a vehicle under arbitrary, unsafe control inputs. Additional information on the implementation, including details on the vehicle model and the terminal set computation, can be found in the accompanying paper, and further research on safe learning and control can be found on the group's webpage.